Morning. All right, let's talk taphonomy. So taphonomy is just how you become a fossil. Essentially, mix of orthogenesis and diagenesis. So orthogenesis is basically how rocks form. You get minerals close together, you apply pressure, you apply some heat over time, which can come from just the pressure basically. Squeeze out the water, and then all of a sudden, atoms that were next to each other are given enough energy where they can actually form bonds and crystals and interesting things. And so orthogenesis is basically making minerals in sedimentary rock. At least the part of orthogenesis that we are going to consider. And then there's diagenesis, which is the way that something is there, it dies, and then these are the ways that it is changed by the process, basically the same process as orthogenesis, of being around those minerals in the rock, and then you'll get new combinations, you'll get alteration, you can get complete replacements, like, if there's a shell there, it may dissolve and be replaced by essentially a cast in, various minerals. So, those are big concepts in fossilization. And they're two sides of the same coin. Orthogenesis is going to affect diagenesis, but at the same time, the fossil may dissolve completely, and the minerals in the fossil, like the phosphate in the nucleus, may become phosphate minerals by binding to something else. So, kind of like that. So, what we're here to talk about are different types of taphonomy, which you can recognize with your eyes, and that's the rest of this talk, so have a look. These are the big types. So permineralization is going to be, the most common type is silica permineralization, where you are basically just filling in all the empty space. You're draining out all the water from an organism or from its remains and replacing that with usually silicon dioxide. That's how you make most petrified wood, and that's why it looks so glassy and beautiful when it's cut and polished. Yeah. Carbonization, you're going to see basically just a carbon skeleton. So you're going to have an organism, the organism is going to get flattened, and a lot of the other minerals are going to get leached out that used to make up the organism, and you're going to be left with mostly a carbon skeleton. So, pardon. Yeah, permineralization is filling in, like you take spongy wood and you fill it in with glass. Replacement is where you take something that would have been hard originally, solid, and it used to be calcium carbonate, but over time, like in acidic conditions, that'll get dissolved and silicon dioxide will get laid down in the same spot because there's like a little hole where the shell used to be in the rock. And you will make a perfect little cast, basically, in a totally different material. So that's replacement. Recrystallization is like when you're replaced, but by the materials that just dissolved. So let's say you have a shell made of calcium carbonate. Let's say you get acidic conditions, so it all dissolves. Let's say there's something about the clay around it, it's like super fine grained, and there's no way for the calcium carbonate to get out. So it's just trapped in there. It's just like liquid calcium carbonate. Then eventually the acidic conditions go away, it dries out a little bit. And so what's going to happen? Well, all the calcium carbonate reprecipitates and it just forms the lowest energy state, which is little crystals. And you get little calcite crystals replacing the inside. So it's like a mold on the outside, but just like a little crystal geode on the inside. They're very pretty and scientifically almost useless just because everything is gone. Whereas with permineralization, you can still have individual cells there that you can see and recognize. Carbonization, you still have a lot of organics there, and so you can do tests on those. Mass spec, X-ray things, Raman, and you can detect some of the chemicals and their alteration products. Replacement can be okay depending how it's done. You can get really nice fossils that are also really easy to get out because if you have a carbonate rock and your fossils have been replaced by silica in there, what happens is you can just drop that whole rock into a giant acid bath, sometimes leave it for years, and at the end, all that's left are your fossils. Yeah, you can dissolve all the rock away, which is pretty crazy. So some of the best fossils come out of that because you don't have to chip them out of the rock. You can just dissolve the rock away, and all the delicate parts stay there. All the little babies are still there. Ah, they're just beautiful. Okay, next we've got impressions, which is just like a mold. You know, the hollow space in a rock where a fossil used to be, and so if you split the rock open there, you'll see the two sides of what used to be the outside, basically. And that's an external mold. An internal mold is all the mud that's gone inside the organism. The organism's dissolved, and so you can see basically an impression of the inside. You can see if it's a shell where mussels used to contact, for example, may see imprints that some of the organs made while the thing was growing. And then lastly, let's just throw this on here. We got two things. Ichnofossils are trace fossils, like footprints and tracks and feeding traces and waste. Some animals pile up little blobs of waste that are all the same size and very neatly arranged, and those definitely tell you something. And then lastly are molecular fossils, which are molecules that have been altered through diagenesis and are now a little bit different, but still close enough that you can actually recognize them. And there are certain types of molecules you only get from some kinds of organism. And so if you find that molecule, if you find an ergosterol, there's no way that could have come from anything but something with fungal metabolism. Yeah, because they're the only things we know that make ergosterol. Or I guess maybe a crown group that was able to do that and then evolved into multiple things. Who knows? Yeah. But it's like a terminal process along a biosynthetic pathway. And it's the point where, like people and plants and fungi are going to start with the same pathway. There's a molecule called squalene, and then they'll modify, and they'll have all the same steps. Oh, fantastic. Celebration. Until they get to a point where each of those things is going to put one final modification on or two final modifications, and that's where they diverge. And those modifications are very specific to a certain type of metabolism. There you go. More explanation than you wanted. All right. Let's talk different types of taphonomy. Ediacara Hills. Nice place, Australia, from the Ediacaran period. Yeah, named after the hills. Nice. So shown here, what you get is death mask preservation, which is where you have an organism that's sitting here, and then sand comes in over the top of it and smushes it a little bit, so you get a flattened version of the organism, because it always gets crushed by sand in Ediacaran preservation. And then the organism dissolves, and so you're left with a cast like that of where the organism used to be. So it's like an upside down, inside out little cast. Yeah, and that's Ediacara preservation. There's fantastic stuff in there. So this is a Dickinsonia. We'll learn about that later. And so here's a Dickinsonia, and here you can see it's offset from a Dickinsonia size and shape little imprint that's much shallower. So we think this is the actual body of the organism, and this right over here is probably its feeding trace. And you'll find several of these little holes in various states next to where the actual body fossil is, which tells you that Dickinsonia was able to move and was able to dissolve the microbial mat it's sitting on. So in the Ediacara Hills, we have microbial mats are thought to be what's covering the ground, basically. This is before there was any real tunneling, burrowing, digging. That transition where organisms start to bury themselves, that marks the beginning of the Cambrian. There's a particular U-shaped fossil. It's an ichthyofossil. We'll cover it in that lecture. And that one marks the bottom of the Cambrian. So body fossil, trace fossil, right there next to each other, but both of them are just molds of them. Here's a Kimberella quadrata. We think this is a primitive mollusk, and look at all these little R's or rake marks. See, they're all like little teeth. And so this is the organism. We think it has a radula, just a little, like a little rake, a little raspy tongue, like you get on a cat. Yeah, and it's going to reach out and it's going to scrape that delicious slime into its mouth. And so here's our Kimberella, and here is the little pattern where it's scraping all that slime into its mouth. Bless. Yeah. But yeah, so you get both ichnofossils and organisms preserved in death mask in Ediacara type preservation. Yeah. There are other fossils from the Ediacaran period that show different types of preservation, but this is what you get in the Ediacara Hills. So, yeah, that's why we'll use that word. All right. Here's an example of internal mold preservation. So here is the material around. This is just the minerals that it's fossilized in. The black parts are going to be actual hard parts of the animal. And you can see how the mud has basically filled in all of those spaces. And so it's kind of like an internal mold. You can see where the organism would have been because that's where the mud has filled in, where all the organism parts rotted away. And you get, yeah, fantastic preservation sometimes. This one's a slice basically through, I think, along this sort of plane, an animal like this. Yeah, you can see its little legs and stuff. I don't think you would be able to identify it from this slice, but what they did was take slice and then keep slicing all the way down and then reconstruct those in 3 dimensions, and that's how you get something like that. But yeah, a lot of times internal molds just look like the inside of a brachiopods or the inside of a bivalve mollusk. There's a little brachiopods up there for inspiration. Yeah, and yeah, that's a pretty common thing. It's okay; those are still useful. They're still worth picking up because you can sometimes see details that would have been difficult to see from the inside of the organism. You can tell what the inside looks like. And yeah, just like in everything else, you can't always judge a brachiopod by its cover. You gotta look a little deeper, look inside if you want to really see what it is. Yeah. All right. Recrystallization. Here was a beautiful shell with a nice, yeah, shell on the outside of it. And something bad happens, like probably acidic conditions. The shell dissolved for the most part. Couldn't go anywhere because this was probably in a really, really fine clay, like marl, like you get down in Florida. And so it was just trapped there and then eventually dries out. It forms beautiful little yellow crystals with some sort of impurity in there, but yeah, that's it. Here is a coral that has kind of dissolved from the inside. Look, it's hollow. It looks like little caves with stalagmites and stalactites. And you've got some parts of it that are nicely preserved, silica preservation on that. And then you've got a lot of infilling on the area that dissolved and mostly left. So this is like silica recrystallization on on the top, and I think this is carbonate. This is calcium carbonate recrystallization on the bottom, I think. And you can see you've got all little layers and stacks and pores, and you've got the animal on these parts that are not recrystallized. And on the recrystallized parts, you have really pretty crystals. So, is that a good trade? I don't know. I don't think so. Shown here is a slice through an arctophyllum, and we're hitting it with UV. There's some heavy metal atoms in there, we think, probably uranium, and that makes it fluoresce like crazy. And here you can see, here's the original parts. So this was originally, we think, aragonite. And then on the outside, it dissolved a little bit and then recrystallized a little bit. And so here's the dissolved and recrystallized part, is this really bright band around the outside with sort of jagged edges. That's the recrystallization. And you can find fossils like this that have 5, 6, 7 layers of recrystallization on the outside, getting a little thinner each time. And that just shows that they were kind of soaked in water and then maybe lifted up, so they dried out and then soaked in water. which may not be the land rising and falling. It just may be the water levels rising and falling, which is definitely a thing that has happened a lot. All right. So that's recrystallization for the most part. Although this would be kind of like a crystallization after it dissolved. So it's like it recrystallized and then a different mineral came in over the top of it and either replaced or coated, yeah, the recrystallized part. So that one's weird. Yeah. Replacement can happen with silica. So here's a little coral that got replaced, and it'll be pretty good as long as you don't look too close. Like here's a little brachiopod, and you're like, oh, that's pretty good because this thing is like this big. So it's preserved a lot of that detail, a lot of those little parts. Then you get closer and you say, oh, what is this? We've got all these little rings in here. It's like, Target logo branded. That's, I believe it's called beakite. Yep, here we go. Which are little ring like formations that you get in silicified organisms that used to be calcite and were replaced by silica. And the process happens like so. And this is a permineralization. So this would be back here. This would be replacement, where you have a thing that was solid calcium carbonate that is now gone, but we've had essentially a glass mold of that has sort of precipitated in its place, and it preserves really great detail. So I think the detail is not from it's not like the original specimen. The detail is preserved because the original specimen made a very detailed mold. So this had to be in a very fine-grained sort of rock. So that, once the original one was dissolved out of there, you could refill it in with silica, and just beautiful. Yeah, preserves even the fine little striations of the detail. Permineralization, yeah, spongy thing, and if you're in conditions where silica dissolves and then you shift to conditions where silica precipitates, so like from high pH to low pH, then you can get silica precipitating inside. It'll basically, there'll be, instead of water being there inside the log, you'll get silica water there because that's what's in the water. And so that'll, permeate in there. It'll all normalize out. And then as that dries out, you will get the silica basically being deposited everywhere that water used to be. And you'll get this beautiful replacement, rather permineralization, which is infilling all the spaces in the organism with a mineral, and typically silica based. So yeah, you could say permineralization is like, there's not a hard line necessarily between replacement, permineralization. All these things are part of the same processes. You will rarely see a fossil where there is one and only one type of preservation. These are more like concepts that you can get and then you can apply, and you can say, oh, here's the evidence for permineralization. Like, look, it's been turned into silica. Here's the evidence for a mold preservation because it's still three-dimensional. Here's the evidence for carbonization because on that little three-dimensional mold that's filled in with silica, there's a fine layer of black stuff, which is probably the carbon from the original organism, like original organic remains that you could analyze for their biochemistry. So yeah, these things are always stacked up in real fossils, because real fossils are rare and they happen when usually not one but multiple things go right, wrong, or go unusually. Yeah. All right. Here's the coolest one. This is opalization. So in opalization, you're going to get silica replacement, but it's going to happen in layers. And in between the layers, you're going to have lots of little water molecules. And so you're going to get these flat layers with thin layers of water molecules between them. And it's going to create an effect just like when you get a thin layer of gasoline or something sitting on top of a puddle. You get that awesome rainbow effect, that Schlerin pattern, I think they call it. And you can get entire gigantic fossils completely replaced with beautiful, beautiful opal, essentially. If I remember right, I think they have a very big one of these opalized ammonites in the Houston, whatever they call their natural history museum. It's something other than natural history, but that's fine. That's their deal. Yeah, we know what it is. Yeah. You can get opalization of a lot of stuff. And remember, this is replacement. We've lost at least some of the original minerals. These are all bones, which are not calcium carbonate. These are calcium phosphate, like your teeth, like your bones. And yeah, they've been replaced with just gorgeous little thin layers of silica. It's the coolest thing. Yeah. There's a couple of places. The big one, I believe, is in Australia, where all the fossils that they pull out look like this, and they're just magnificent. The idea is that for when you are replacing with silicon dioxide, so there's all these different forms of silicon dioxide, like agate is kind of a messy form. Quartz is just a very pure form. It's just like they're literal glass crystals, yeah, just with a different crystal packing that you don't often see. Like glass that we look through tends to be an amorphous liquid, if I remember right. It's like almost solid, but not quite. Yeah. But yeah, you'll. They've actually figured out how much time you need and how much temperature you need. And so as you increase the temperature and increase the time, you're going to move things toward quartz, basically. And so things that start out as opal are eventually no longer going to be opal because we're going to keep heating them up, driving the water out, compressing the layers down until they actually join together. And with all that pressure and all that time, eventually the molecules that were arranged in little sheets will find a crystal or way to arrange themselves. And yeah, the crystal version is what we call quartz. Really, is there any difference between these? I don't know. Not fundamentally. They're the same molecule, just stacked up in a different way, so that it looks different to our eyes. But honestly, it's like if you have your dinner and you make a little pile out of the peas versus if you have the peas all spread out. You still got to finish your peas. Yeah. That's the moral of today. Okay. Here's another famous site with a different taphonomy. So, Solnhofen Quarry, which is in Germany, the Solnhofen limestone doesn't have very many fossils, but the ones it has are really something. So all of the Archaeopteryx fossils, this is the transitional thing that's kind of, it's still a little dinosaur, but it's got feathers like a bird, and it's really on the way toward being what birds are today. It's a lot closer to birds. But anyway, yeah, all the fossils of these things come from this one particular quarry. Yeah, and there are even a couple fossils of just their feathers. So here, have a look. You get preservation of the bones. So the bones have stayed there, and hard parts, I believe, stay there. But you get impressions of a lot of soft parts, like feathers in this case. So it's a mix. The cavities of the bones have filled in with quartz. Do you remember the fancy word for what filling in with quartz is? Yeah, or silicon dioxide. Permineralization, right? Silica permineralization. Yeah, yeah, yeah. It's not hard. Yeah, you got this. Yeah, yeah, they have very fine mud in very thin layers. Okay, shown here, pyritization is beautiful and sometimes produces very good fossils. You will get pyrite replacement, which is basically your original fossil is coated in metal and then replaced by metal. Iron pyrite is an iron sulfur compound up there. Sometimes you get little crystals of it on the surface. These are two little brachiopods looking gorgeous. And they look great as long as there's no water and no oxygen around, because if you take an iron compound and you expose it to oxygen and water, it's going to get oxidized and it's going to turn to rust like this. And so a lot of times you'll break open a fossil and it'll look like it's rusted out inside. You're like, what? This thing wasn't made of metal when it was alive. But that means it was preserved probably by pyritization, partial or complete. And then through diagenesis, the pyrite turned into an iron oxide, basically, which is just a fancy word for rust. So yeah, you get pyrite formation with very low oxygen. Duh, yeah. So anoxic environments, and you have to have a high amount of sulfur there. They tend to happen, if I remember right, in fresh water more commonly than in salt water. Um, yeah. And if you look at super ancient fossils from the very early Earth, when the continents are just forming, there is a lot of iron and a lot of sulfur there, but there's no oxygen. This is before organisms released most of the oxygen that's now in the atmosphere. And so things didn't oxidize. And so you had rivers that were just water running down little pyrite pebbles, little golden rivers of the long, long ago. And you can find these fossilized or traces of them, and it's pretty cool. But yeah, to see something like that would really be something. But you can't both see that and breathe. So yeah, you got to think about that when you're making your time machine. If you go back too far, there's no oxygen, and you're going to have to bring like a scuba tank or something. So, let's see some realism in those time travel movies, please. Okay, another place where you get awesome pyritization is in the Hunsrück Shale in Bundenbach, Germany. And we do have one fossil I purchased from here. And yeah, this is essentially a metal replacement. And the cool thing about pyritization is that it's done by bacteria, we think. Will at least start off the process, and then once you lay down a little bit of pyrite, if there's the dissolved components in the water, they will potentially crystallize onto that. They'll just be deposited on top. But you get basically metal replacement of even the soft parts of an animal, and because of that, you can actually X-ray these, and the metal will show up on the X-ray, just like bones show up on the X-ray. And you'll be able to see through the rock, and you'll be able to see in 3 dimensions all the parts of these things. So here's an example. There's a trilobite fossil where you can actually see its legs dangling down, but you can X-ray this bad boy, and you can see the legs on both sides. You can see everything that's going on here. You can see its internal organs to some extent. That's pretty cool. Here's a scorpion, and here's the scorpion with X-rays. So there you go. Carbonization, a thin black film, virtually flat. You can get carbonized insects, you can get carbonized leaves, you can get carbonized anything that used to be organic and made of mostly carbon. You can get some preservation of soft parts. Carbonized fossils are 3-dimensional. They will retain that. So you will have, because it's flattened down so much, you will need to microscopically dissect if you want to tell the top layer from the bottom layer, because these things are very, very thin, like, atoms thick. Yeah. It can be analyzed. So there are changes that happen. You can actually simulate carbonization. So we figured this out. If you take things like feathers or insects or whatever, and you subject them to pressure, so a certain amount of pressure, like you would get if an entire mountain's worth of rock has formed on top of you and is basically crushing you forever. And then generate a little bit of heat in that, and you can actually, look at that. So with low heat, you get this sort of brown to black. This was a black feather originally. And here's an iridescent feather. And so they'll all change. They'll all look fairly similar. And then as you heat them up, they'll actually undergo different changes. And then once you get them too hot, you will get complete. So you'll get stability, polymerization, where you sort of join molecules together, carbonization, where you've kind of destroyed the structure, but you do have the carbon that's left there. And then you'll get decarbonization, where the carbon molecules, it's actually too hot for them, and they will either combine with other things or just get boiled out of the rock, basically, and oxidized until they just go away, CO2. And then you just get an impression, which is basically a mold. If we find fossils and they still have organic remains in there, the temperature wasn't that hot, and the pressure wasn't that much. Like it got some rock deposited on top of it, but it was pretty close to the top of the stack. And yeah, they make great fossils when you can find them. Yeah, it's just they don't always fossilize that way. Okay, next one, because why should there not be a next one? Phosphatization. Look for that red color. This color right here. That's what phosphate preservation looks like. We'll be looking at a lot of little nodules that have phosphate preservation. Phosphate preservation gives us extremely good, even sometimes cellular or subcellular preservation of biological structures. So it is really nice. Here are some phosphatized fossils, and you can actually still see the organization of the muscles in little bands. And this is all just like phosphate replacing most of the organic materials. So it starts out as a phosphate coating and then a little bit of phosphate replacement. But wow, is that fine grained? So the chemistry of the thing has changed in phosphatization. You may lose some of the organics or combine them in weird ways that are hard to untangle, but you will get amazing preservation of the structures down to very, very tiny levels. And so that is immensely, immensely useful. Really cool when you see it. Okay, so this is just talking about distribution of where do you see phosphatization, where do you get exceptionally phosphatized fossils. And so here are some. Dushantuo in China has these little embryo fossils. You got the one where it starts as one cell, then it divides into two cells, and then four cells, and then 8 cells, 16 cells. It's just like a little baby being born. We don't know what the creature was. They are only found as embryos, so it could have been just something that, that was its development. It was like, hey, I'm 32 cells. Yeah, look at me. Yeah, what have you got going on? Or it could have been that they continued to differentiate into something else. There must have been some point though where it was just like, like one cell differentiates into two, and now it's like two cells, and we can cooperate, and so that's probably an evolutionary advantage. But yeah, here's some of the others that you get in there. So you will get sometimes a little bit of phosphatization in the Burgess Shale. Although usually that is Burgess Shale type preservation, which is you essentially lose all the hard parts and you get silica replacements sometimes of some of the hard parts, but you'll get carbonization and impressions that preserve even the soft parts. So it's still pretty darn good. I'd take it for sure. And here we go. Yeah, just up through time, you get all these other ones that are very interesting. And so that's where we know you get phosphatization. Where's the next place? Because there's phosphate all over the place, but you need phosphate in a place that had a lot of animals or plants or something in order to get fossils that we can see. And then you need somebody to find that and describe it. So there are certainly more exceptionally phosphatized places out there, like a lot of Canada, geologically unexplored, a lot of parts of Alaska, barely explored at all. So there's cool stuff out there. Yeah, just gotta keep looking. Here are some of the embryos from Dushantuo and some of the other weird, like little tiny jackfruit, just a couple of microns wide. But yeah, perfect little fossil with little spikes coming out of these little mounds. I don't know what to make of that. And this thing, it looks like a crazy sort of nut. But these are tiny animals, and they show organization, and they're interesting. Here's a lobopodian that is phosphatized. This is from a thing called the Orsten, which J, K, and L, which I want to say is somewhere in Scandinavia. But it's a little bed where you get these tiny nodules, and if you dissolve them away, there are phosphatized creatures inside. And the phosphatized minerals won't dissolve in the same acids that dissolve the rock around them. So it is possible to just put some acid on there and then pick out the amazing fossils. You have to sort through a lot of trash. It's not just like only amazing fossils, but yeah, the things you find, wow, wow, yeah. Okay, phosphatization. So here are little muscle, basically little sarcolemmas from muscles in a crustacean. And you can see that, yeah, you're starting to get little calcium carbonate dumbbells that are overgrowing basically the cell bodies here. But you still have preservation of some of the muscle fibers because phosphatization is awesome. Um, yeah, and here's another case of a beautifully preserved little three-dimensional worm. And you've still got the different layers on here. And if you look at the outside of this, it's actually made up of these fibers like that. It's pretty crazy. I think those might have been little chitin fibers on this worm. And it's super old. It's Ediacaran, so pre-Cambrian. Yeah, they found these things by drilling boreholes down to, like, get a stratigraphic column of the rock. And yeah, in there they find all kinds of crazy stuff. You crack those open, you get all these deep layers that are not exposed anywhere. And if your drill happens to have hit where a fossil is, then you get those fossils that nobody else could have got. Yeah. You're kind of drilling blind, so it's not likely that you find anything. But when you do, yeah, it's always something kind of neat. So there we go. That's the end of this one. That is taphonomy. Most of the end of this was just me talking through, here are some examples of the different types of taphonomy, but the real meat of the thing is slide 1. Learn those 7 or 8 types of taphonomy, and then the rest of the slide set will show you how to recognize those and what to expect from those, because that's worth knowing, because this is how fossils get made. That, and make sure you know orthogenesis and diagenesis, because those are going to come up a lot. And I want to make sure when I use the word, you're like, oh yeah, I know what that means. Yeah. Which it takes a minute. All right. Thanks a lot.